Welcome to binary trees. We'll talk about these for a while and we'll eventually get into binary search trees as well. But here we're just talking about binary trees. So binary trees are rooted trees. And I'm going to abbreviate these BTs sometimes, not always. But yeah, BTs are rooted trees. The rooted trees and the nodes have at most 2 children. Okay, there's never going to be 3 children. And specifically, each child is either a left child or a right child. And that's even if there's only one child. Okay? So that's all a binary tree is. That you have at most 2 children, and you very clearly specify, again, here for rooted trees, spatial orientation matters. You specify which one's a left or right. So going back to these, this is not a binary tree because it's not a rooted tree. This is almost a binary tree, right? Every node has 0, 1, or 2 children. And there are mostly left and right children, except for right here. I didn't specify whether C was a left or right child. So, if we make one small adjustment here, now it's a binary tree. We could have also made it a right child as well, and it would have been a binary tree. This is maybe obviously not a binary tree, right? C has too many kids. So that's what binary trees are. So binary trees, are rooted trees with the following properties. And we're going to do some traversal. So binary trees are graphs. We already talked about how to traverse a graph, right? We can do breadth first, in which case, right, we'd go like A and then either F or B and then C and then either E or D and so on, right? Or we could do depth first, where we, again, choose a direction and just go all the way down. For binary trees, we're going to have 3 algorithms that we talk about. And yes, we can traverse these with the previous ones, but these specific 3 algorithms are going to be useful in terms of like searching. And it's essentially not so much that we care about that it's hard to traverse trees, because it actually is quite easy to traverse trees. You could make your own algorithm very, very easily. It's more about, can we do it intelligently in a way that saves computational time, specifically for searching applications. The order in which we traverse things is important, even if, right, traversing itself is not going to be very hard. The order will have different benefits for different things. And remember, when we traverse trees, we do something called visiting a node. That really depends on what the point of our traversal is. In Dijkstra's shortest path algorithm, right, visiting was a pretty involved step where we eventually looked at things and we found the cheapest thing. We'd make an arrow. We have to erase arrows. We update values, right? So the order in which we do things does matter. And that's why we're going to talk about 3 orders of traversing. Again, traversing these is not hard. Sometimes traversing messy graphs can be hard, but traversing trees is pretty easy. We're just going to do it efficiently, essentially, for applications. And we're going to talk about 3 ways of doing that. Spoiler alert. I already gave you a spoiler. That's one of them. Pre-order. So we can traverse these binary trees. Traverse binary trees in 3 ways, right? Pre-order, that's what we're talking about here. Well, if there's pre-order, what do you think there is as well? Yes, post-order. And the last one's going to be in order. You ready to go? Let's talk about pre-order. Here's the algorithm. Pre-order, binary tree traversal. Step 1. Visit the root of the tree. And remember, visit depending on what algorithm we're doing, what application we're doing, why we're traversing this node. Visit can involve quite a few steps, but here we're just going to be marking it down as, yeah, we visited it. And then we treat the left child, because again, for binary trees, every child is either a left child or a right child. Treat left child and its descendants, so everything under the left child, as a subtree. So we're going to treat the left child as its own tree. And then we traverse it. How are we going to traverse it? By going back to step 1. So then we have a smaller version of the problem, and we go through this algorithm, which will break it down into a smaller version of this problem. We'll go through the same algorithm, and so on and so forth. We're breaking this down into smaller, similar problems, and doing that. This is a recursive algorithm. Okay? Breaks the problem up into smaller problems, which is, again, very common in like programming as well, right? You have a function. What do you need the function to do? Well, you need it to do all these things. We'll break it down into, smaller functions to do it. We declare those functions and so on and so forth. Step 3 of this algorithm is basically the same thing, where we treat the right child. Oops. I didn't write the word child. We treat the right child and all their descendants as a subtree, and then we traverse. So the same thing as step 2, just with the right child. And remember, there are only 2 children at most in a binary tree. That's the algorithm. Let's traverse together. If you're feeling bold, go ahead and pause the video, try it all on your own. Or if you want to see the first few steps, let's do it together. So the first step is to visit the root. What's the root of this tree? It's G. We have visited G. What's the next step? Treat the left child and its descendants as a subtree, and then we traverse. So we're zooming in now on this subtree, right? Which is a tree in its own right. This is a tree with K as the root. And we go back to step 1. Step 1 said visit the root. So we said, okay, we visited the root. K was next. And then step 2 was look at the left subtree and do the algorithm again. Go back to step 1 again. We're going to visit the root again. So I'm going to not have 5,000 subtree boxes here, but yeah, we're visiting the root again. So D was next. Step 2 was look at its left child and traverse. D doesn't have a left child, so we finally get to move on to step 3, which is visit the right child, treat this as a subtree, and traverse. So you can see, right, we're going to go to O, and then visit the root. There's no left children, so we're going to go to I. Visit the root. There's no left child. There's no right child. We finally went through all 3 steps on a subtree. So now is confusing because really, right, there are so many boxes here. There was this subtree, and then we looked at this subtree, and then we look at this subtree, and then we looked at this subtree. Well, we finished the black subtree, and now we've just finished the red subtree, and now we've just finished the green subtree. So we're back. If you can think, right, we were nested so many layers deep, but we're now back in this yellow subtree. Step 2 was treat the left child and its descendants as a subtree and traverse. Well, we can finally do step 3 for this yellow subtree. All right, step 3 says look at this right one. So we're going to visit M. And then its left child C, its right child E. And now we're finally done with this yellow subtree. We're back to the main tree. And we now move to step 3 for the main tree. So if you follow this algorithm, right, you should get H is next. I'm running out of room to write. So let's continue the order here. H, and then A, and then B, and then F, and then N, and then L. It's pretty much I actually haven't checked whether it's identical, but it's pretty much depth first traversal. But we just always go left first. And that is this algorithm. To me, this is the simplest algorithm. The other ones are a little bit weirder to me, but there are also ways of making sense of them. But let me know if you have any questions. That's this video. This is pre-order traversal. Stay tuned for post-order and in order. I was going to say you don't want to miss them, but are they really that interesting? Sure, they're that interesting. Yes, because I'm teaching it, I'll say they're that interesting. Bye.